This conference will now be recorded.
Very good evening, students. So yesterday we had discussed about current voltage relationship in case of pure inductor in AC circuit. I'll just recap a bit and then I'll discuss about pure capacitor. When a pure capacitor is connected in an AC circuit, then what will be the current voltage relationship? And today we'll take up few numerical problems depending on the topics we have covered, like average current, like average quantity of AC or alternating quantities, then RMS quantities. What is the value of RMS value we have to calculate, and then we had already discussed about pure resistor. When we connect a pure resistor, what is the current voltage relationship, and we had seen what is the current voltage relationship when a pure inductor is connected in an AC circuit. So today we will be discussing mainly this pure capacitor. When a pure capacitor is connected in an AC circuit, so what will be the current voltage relationship, and we will just see the comparison of all the parameters we had learned so far. Then we will take up numerical problems. All right, so let us just recap a bit about yesterday's class, a little bit. See, if excuse me, if an inductor coil is connected to an AC source, then we had seen by Kirchhoff's law we can write L di dt is equal to, if the voltage source is sending a signal V0 sine omega t, then we get L di dt is equal to this V0 sine omega t, and from there we had just integrated. So di is equal to V0 by L, okay, V0 by L sine omega t dt, and integration 0 to I di here, and here integration over t. Okay, so actually this, okay, so right hand side sine omega t dt, and with the integration constant, and as you know this will bring you cos V0 by omega L cos of omega t. When we get cos of omega t out of integration, then one minus sign comes. This is C1 and here it is I. Okay, so to absorb this minus we have to make it sign, right? Omega 0 by L, sorry, V0 by omega L, this sine omega t minus pi by 2. So this will bring you with minus sign in front, and this plus C1. And see, these are all, see, this is actually time varying. We are just talking about time varying quantity. So if you take this average, this time average, this doesn't mean anything. Okay, this doesn't mean anything. So since it is not a time varying quantity, this we are not considering as a quantity. So this C1 is a constant quantity. Okay, but we are interested in alternating part of the current. So see V0 by omega L. So this part I can write this has dimension anyway. This has dimension of current. We wrote I0. I0 means peak value of the current. Peak value of the current. Peak value of the current. Okay. So this is I0. So if this is current, see this is actually voltage, and obviously then this is actually effective AC resistance. Okay. Effective AC resistance. AC resistance in inductor. Okay. AC resistance. Right. So effective AC resistance. So this has dimension of resistance omega L. Omega L actually is called inductive reactance. Inductive reactance. Omega L is denoted by XL, and it has got a name, that is inductive reactance. Inductive reactance. All right. So this is what we had discussed. Now see, when you have this V is equal to V0 sine omega t, this is the source voltage which is sent in the circuit, this one, and the current what we get, I is equal to I0 sine omega t minus pi by 2. So this is what we get, sine omega t minus pi by 2. That means what? Just by looking at the equations of this current and voltage, you can see that the current is lagging behind the voltage, source voltage, by 90 degree or pi by 2 radians. And see in the phasor diagram, this is a phasor diagram. So we see this is the voltage which is actually pi by 2 ahead of this is pi by 2 ahead of the current, right? So there is a pi by 2 phase difference here. Okay, pi by 2 phase difference is there between the voltage, source voltage, and the current in the circuit. So that's why, see, in the phasor diagram, we know the instantaneous quantities, alternating quantities can be represented by rotating vector. So we have drawn this blue one as the phasor of voltage and red one phasor of current, and see current is 90 degree behind the 90 degree away, and it is actually behind the voltage. So that's why this I is drawn in this, like in this fourth quadrant, and this has been drawn in the first quadrant. Okay, so this is what we have learned yesterday. And one more point, see this one. Let me just erase this part, or otherwise it will be difficult to explain here. Or just a minute, I'll keep this figure some clean portion. Okay, all right, now we'll see here. See, this is XL. XL means omega into L. Omega into L. Omega is angular frequency. So omega L means 2 pi L into F. F is the linear frequency. 2 pi L into F. L is the inductance. 2 pi. This is in radian. F has its value frequency. This is a linear frequency. So as the frequency of the alternating source voltage increases, what will happen? This omega L, what will happen to this omega L? Omega L also will increase. So that's why, see, we can say if the variation of the alternating quantity is much faster, more the resistance is offered by the inductor coil. That means it will oppose more and more if the frequency is increasing. So this is what you look here. So as the frequency increases, this inductive reactance, inductive reactance increases. That means what? Inductor coil will offer more and more resistance to the flow of the current. And see, when F is 0, the frequency is 0, that means for DC. For DC current, it does not offer any resistance. Because when F is equal to 0, then omega L or XL also will be 0. If F is equal to 0. Okay. So that means what? Inductor coil only will offer or oppose the alternating current. The alternating current, it cannot oppose the DC current, or this current will not be having any effect. Okay, it doesn't actually. So omega L will be 0 when frequency is 0. All right, so this is what we had planned yesterday's class. So today we'll be learning about the current voltage relationship in case of pure capacitor when it is connected in an AC circuit and an alternating voltage V is equal to V0 sin omega t is supplied. Okay, then what happens? So suppose the capacitor, so capacitance of the capacitor, is C is equal to, is C. Okay. So we know that the charge flow in this, or charge stored in this capacitor will be, if the charge is Q, then Q can be written as V instantaneous voltage into C at any instant. If at any instant of time the charge stored in the capacitor plates in the capacitor plate is Q, then Q is equal to CV or VC. So I can write Q is equal to, this voltage is how much? V0, C V0 sin omega t. Now I need to find out the current through this circuit. So how to find out? I can write, in the figure it is written I. So this I is equal to dq by dt. Okay. Then CV0 omega cos of omega t. Okay. So this is actually current, and you look, this can be written something like this: V0 by 1 over omega c. Because this omega and c both are multiplied in the numerator, this is cos of omega t. Okay. So this cos of omega t, since I have voltage, I'll write once V0 sin omega t. I need to find out the relation between this. This is equation number 1. This is equation number 2. So this, let us write little bit modified way. Omega t plus pi by 2. Okay. So this will actually here 1 over omega c. let me just write neat and clean. So in this case, see, this is I. That means, you know, this. Okay, let me write in this side. If I write this term, this particular term as I0, the magnitude of the current in the circuit, then it is, and see what is this I0? I0 is V0 by 1 over omega c. So in this case, you look, this is V0 has dimension of voltage, but this has dimension of resistance. Excuse me. Dimension of resistance 1 over omega c, that has dimension of resistance. But this is not, say, since in DC we say resistance, in this we will not say this quantity as resistance, we will say capacitive reactance. So the reactance and the resistance, both are actually the having same role. So the role played by resistor in DC is played by reactance in the AC circuit. This is capacitive reactance. Okay, and you can see this capacitive reactance is actually denoted by capacitive reactance is denoted by XC. XC is written as 1 over omega into C, okay, or 1 over 2 pi f into C. So this is actually capacitive reactance, and it also has the unit ohm. Okay, now see, the point is here we have voltage V0 sin omega t. V is equal to V0 sin omega t. This is the source voltage which is sent through the capacitor. But what is the current we get? So we see this term here, V0 by 1 over omega c. I0 is equal to, and see here what happens. This is sin omega t, this is sin omega t plus pi by 2. That means the current is actually ahead of the voltage, source voltage, And how much ahead? It is ahead of source voltage by pi by 2 radians or 90 degree. Okay. See in this figure, this is actually the current. This is voltage. Okay, so current is actually ahead of voltage by pi by 2 radians. So see, this is the phasor diagram. This particular part is phasor diagram. This phasor diagram, see, this is the current, this is the voltage. Since current is 90 degree ahead of voltage, so this is the figure. So current is 90 degree or pi by 2 radians ahead of voltage. Okay, so this was about capacitor. And say if we draw the capacitive reactance, since it is X, so since this could be written as 2 pi f c. Okay, so as the frequency increases, in this case the capacitive reactance decreases. Okay, so this is about capacitor in an AC circuit. Now we'll just move on to the numerical problems. Sorry, before that we'll just see all three components. So whatever we have learned, like resistor, capacitor, inductor, all three components, they like what are the voltage drop across them, peak value of the voltage drop, and what are the value of resistance or inductance, sorry, resistance or reactances, and in which cases how much phase difference is there between current and voltage. See, if I take the resistor, see here in AC circuit also Ohm's law is Ohm's law applicable. Okay, Ohm's law is applicable here also. So V0 is equal to I0 into R. Okay, and circuit quantity is resistance here. Resistor actually resistor provides resistance only. That is, in AC also it is resistance, and DC also it is resistance only. Now we have seen from the phasor diagram current and voltage, they are parallel to each other, or they don't have any phase difference. Both, say in a circuit where there is a resistor alone, there the current and voltage, they are in the same phase. current and voltage, they are in the same place. Okay, in the capacitor, see, this is how we can find out the voltage across capacitor. Peak voltage V0 is equal to I0 and XC means capacitive reactance, and that XC is actually here. You look this 1 by omega C. Now inductor, in case of inductor, see voltage is I0 into XL, and then XL is equal to omega into L, omega into L, that means angular frequency into the inductor. Yes, inductance. So this is the case in case of pure resistor circuit in AC. Inductor case we can draw. Inductor case will be this. The current will be lagged compared to voltage. So this is 90 degree. Sorry. Yes, we are here. So this is voltage phasor, this is current phasor, okay? And this is omega t actually. All the business is omega t. And in case of, so this is for pure inductor circuit, pure resistive circuit. For pure resistive circuit, phasor diagram is this and this. I'll just draw it properly. In case of capacitor, it is voltage say, and this current. Okay, so there is a 90 degree phase difference here also, or 5 into radians. Okay, this is about omega into t. So these are actual phasor diagrams for all three components: resistor, capacitor, and inductor. So this is actually for capacitor. All right, we'll just take up numerical problem. So calculate. You can see this figure in the screen. The question is calculate the RMS value of alternating current. You see, RMS value of alternating current you have to find out for the figure where the current is given. Okay, so what we have to calculate? We have to calculate alternating current. Sorry, RMS value of the alternating current. See here, the current is given, how the current is varying. Okay, how the current is varying, that is given. See here, it is, if I take it some time, generally what we do, how do we calculate RMS value? We calculate RMS value by taking, see, RMS means RMS. We just go from last, square it, then take the mean, then take the root of that. Okay, square root of that. So you can see here there are currents. See, up to this, suppose this is time t1, this is up to t2, and this is t3, up to some time. Okay, so this is actually plus 2 ampere, this is minus 2 ampere, and this is again plus 2 ampere. So if I say this current is I1, this is I2, and this is I3, okay, then we can take RMS, IRMS like this, square all of them and take the sum of them. Okay, square then mean. Square means, and we have to take mean also, right? So 2 square plus minus 2 square. I'll just, before that, let me write, maybe I can write I1 square plus I2 square plus I3 square, then divided by 3, that will be square then mean, then root over of that. Okay, so for this we look, so this is 2 square plus minus of 2 whole square, here again 2 square divided by 3, right? Then here you get 4, 4 and 4 divided by 3. So this will give you 12 over 3, that is 4. So you get square root of 4. Okay, square root of 4 out of this. You get square root of 4. Square root of 4 means what? 2. So this is ampere, in ampere. So 2 ampere is the RMS current for the given pattern or variation of the alternating current. Okay. All right. So we'll go for another problem. This is here. Here, this is also related to RMS current only. RMS value of the current, calculation of RMS value of the current. Okay. See here, in this case, the current is varying I0 T by tau like this. You have to actually calculate the RMS value during the time interval 0 to tau. So you know what we have to do for this? We have to actually do this. The IRMS is equal to first of all we have to square the quantity, then we have to take the mean over full cycle, okay, 1 over tau dt, and this also will have limit 0 to t. So this is what we have to actually do. So then what is this I square? We can write it here. Okay, let me just do one thing. Just to avoid too much haziness in the solution, I'm just taking this integration part, 1 over tau integration 0 to tau I square dt. This could be again written as 1 over tau 0 to tau, and this I square means I0 square, which is time independent quantity, then t square divided by tau square again. This is dt. Okay, look here, we can get this is, so this tau has nothing to do with the integration, tau q, and then here there will be I 0 square also. Only thing is that integration will be for t square dt. So this will be written as t square, sorry, t cube by 3, and this has limit 0 to tau. So this tau we can write it here. So I0 square divided by tau cube. Then you have this also tau 0 cube. So this will cancel each other. So I0 square by 3. Okay, I0 square by 3. We can write it here. Or I0 by root 3. So this is how actually you have to solve problems. Okay, so here IRMS is equal to I0 by root 3. We have taken a very simple problem again. One more. So see, a pure inductor of inductance, that means L is given, inductance 25 millihertz is connected to a source, okay, of 220 volt. So this, what is this 220 volt? Find the inductance. I think it is inductive reactance. Okay, it is reactance. Find the reactance and RMS current in the circuit. The frequency is given this much hertz. So here the voltage of the source what is given is actually VRMS 220 volt. Okay, so we have got L is equal to this 25 millihertz, then VRMS 220 by, so 220 volt, and see frequency, this frequency hertz means, you know, this is given in F, linear frequency, so we can make it omega 2 pi F, that means 2 pi, so this is F, 2F into pi, that means 100 pi. This is 100 pi. You have to first find out what is omega L or XL. XL means omega L. Inductive reactance, omega into L. Omega is 100 pi into L. L is actually 25 millihertz. 25 millihertz means 10 to the minus 3 hertz. Sorry, Henry, not hertz. Okay, so we'll be able to find out this if we write 2 pi f, 100 pi it is. 100 into 3.24, 25 into 10 to the power minus 3. Okay, so this, all of them will contribute to the capacitive reactance, and that value will be actually 3.1. So this will be the value if we just type this. So this is the one, okay, 3142 ohm. Okay, we have got capacitive reactance omega into L. Then we have to find out what is RMS current in the circuit. RMS current we have to find out. What is the RMS current? So pure inductor. This pure inductor, right? Then current will be IRMS, VRMS by XL. So VRMS already given 220 volt. So XL we had got already, right? I'm sorry, this XL value, I think this will be some different values. We will just, if we just calculate this, it will be around, this will be in ohm, obviously. This will be something like 7.85 ohm. Okay, ohm. And then you just put it here. So you'll get the current 28.03 ampere. So this will be the IRMS in the circuit. Okay, so with this today we'll stop it here. In the next class we will be learning about LR, combination of LR in AC circuit, then CR, combination of CR in AC circuit. So in the next class we will just discuss this thing. Okay, when L and R both are connected in series in an AC circuit, so what will be the current voltage relationship, and what are the magnitude of or peak value of current or RMS value of the current in both circuits, and many other physics we will be discussing. Obviously we will be drawing this phasor diagrams for respective voltage and current for both cases. Okay, and we'll take up numerical examples as well. All right, so we'll stop it here for today. Thank you for your patience.
This conference will now be recorded.